Hi everyone, welcome to our YouTube channel. In this video, we will be discussing about deadlock and starvation. Now, moving on to what is deadlock. A deadlock is a situation where a set of processes are blocked because each process is holding a resource and waiting for another resource acquired by some other process. Consider an example when two trains are coming towards each other on the same track and there is only one track. None of the trains can move once they are in front of each other. A similar situation occurs in operating systems when there are two or more processes that hold same resource and wait for resources held by others. Related to deadlock in the context of the scenario with two processes and two resources. Mutual exclusion. This condition requires that at least one resource be held in a non-shareable mode, which means that only one process can use the resource at a given time. Both resource 1 and resource 2 are non-shareable in our scenario, and only one process can have exclusive access to each resource at a given time. Next is hold and wait. The hold and wait condition specifies that a process must be holding at least one resource while waiting for other processes to release resources that are currently held by other processes. In our example, process A has resource 1 and is awaiting resource 2. Process B has resource 2 and is awaiting resource 1. Both the processes hold one resource while waiting for the other, satisfying the hold and wait condition. Next is no preemption. Preemption is the act of taking a resource from a process before it has finished its tasks. According to the no preemption condition, resources cannot be taken forcibly from a process. A process can only release resources voluntarily after completing its task. In our scenario, neither process A nor process B can be forced to release the resources in their possession. The process can only release resources voluntarily. The next one is circular wait. This condition implies that circular processes must exist, with each process waiting for a resource held by the next process in a chain. In our scenario, process A is waiting for resource 2 and is being held by process B. Process B is awaiting resource 1 from process A. This circular chain of dependencies causes a deadlock because neither process can proceed, resulting in a system shutdown. To summarize, in the context of two processes and two resources, all four conditions, mutual exclusion, hold and wait, no preemption, and circular wait must be met at the same time. Deadlocks are a major concern in OS, and various techniques are used to avoid them to prevent, detect, and recover from them.
Deadlock prevention is crucial in computer systems. To prevent deadlocks, consider these conditions. Firstly, mutual exclusion. Mutual exclusions means that multiple processes can't use the same resource at the same time. However, while this is reasonable, it results in a deadlock. There will be no process waiting for the same resource if we may use the same resource for several processes at the same time. However, if we can prevent the resource from acting in a mutually exclusive manner, we can keep the system from becoming stuck. Next, hold and wait. Hold and wait condition occurs when a process holds a resource while waiting for other process to complete its task. There is a risk of deadlock in this case because many processes possess one resource and cyclically wait for various other resources to complete their task. As a result, we'll need to come up with a procedure that doesn't hold any resource or wait for any resources. Thirdly, no preemption. No preemption means the reason for the deadlock is that once the process starts, it cannot be stopped. However, we can avoid deadlock by removing resources from the process that could cause it. However, this is not an appropriate technique because bringing out a resource that is used by the process will be inconsistent with the previous effort. Lastly, circular wait. A circular wait occurs when one or more processes wait in a circular order for resource they require. The problem of a cyclic wait can be solved by assigning a priority number to each resource. A resource with a lower priority value can be requested by the process. By following these rules and using techniques like resource allocation graphs, we can ensure our system runs smoothly and avoid the frustration of deadlocks. Deadlock avoidance. Deadlock avoidance involves Banker's algorithm, wait-die scheme, and wound-wait scheme. Firstly, Banker's algorithm. Banker's algorithm ensures resource allocation in a way that guarantees system safety by checking for a safe state before guaranteeing resource request. Wait-die scheme. Older transactions are given priority, while younger transactions requesting the same resource are allowed to proceed. If an older transaction requests a resource held by younger one, the younger one is aborted and then restarted. Wound wait scheme. The prioritized resource access based on the age of transactions. Younger transactions wait for older ones to release resources. If a younger transaction requests a resource held by older one, the older one is aborted and then restarted, reducing the risk of deadlocks while minimizing restarts. Deadlock reduction is a crucial concept in operating systems to identify and resolve resource allocation conflicts. It involves periodically examining the system to detect if a deadlock has occurred. This is typically achieved through various algorithms like the resource allocation graph or the banker's algorithm. When a deadlock is detected, the operating system can take actions like process termination or resource preemption to resolve it. Here are some of the key points of deadlock detection: proactive anticipation, no prevention techniques, stalemate determination, recovery actions, resource allocation graph, single instance resources, and multiple instance resources. Deadlock recovery is an operating system aims to resolve detected deadlocks. It involves process termination or resource preemption. Process termination ends one or more processes to release resources, while resource preemption temporarily takes resources from processes. The chosen method depends on system policies. The goal is to re-establish system consistency and let remaining process continue.
Let us see what is starvation. Starvation in computer systems refers to process or threads unable to progress due to resource unavailability. It can be caused by inadequate resource allocation, priority inversion, or deadlocks. Resource starvation results from the inability to access necessary resources. Priority inversion occurs when lower priority tasks block higher priority ones by holding resources. Time starvation happens when processes don't receive adequate CPU time. Circular wait, that is deadlock, can also lead to processes effectively being starved. Addressing these issues is essential for fair resource allocation and system performance. Deadlock and starvation are two different entities. Deadlock occurs when none of the processes in the set is able to move ahead due to occupancy of the required resources by some other process. Starvation occurs when a process waits for an indefinite period of time to get the resource it requires. Deadlock is also known as circular waiting, whereas starvation is synonymous to lived lock. In deadlock, requested resources are blocked by other processes, whereas in starvation, they are continuously used by high priority processes. In deadlock, no process can make progress once it occurs. In starvation, apart from the victim process, other process can progress or proceed. The four conditions that lead to deadlock are mutual exclusion, hold and wait, no preemption, and circular wait, whereas starvation is caused by uncontrolled management of resources, process priorities, and use of random selection. Deadlock requires external intervention to solve, whereas starvation may or may not require external intervention to provide a solution.